In 1974, a physicist sitting alone in his office in Cambridge did a calculation that should not have been possible. He was trying to combine two theories that had never been successfully merged: quantum mechanics, the physics of the very small, and general relativity, the physics of the very large. Nobody had done it before. Nobody knew if it could be done. And when the mathematics came back, the answer was so strange, so deeply wrong-feeling that he assumed he had made an error. He checked it again. The answer was the same. What Stephen Hawking found that day at 32 years old, already confined to a wheelchair by early motor neuron disease, was that black holes, the most destructive objects in the known universe, the entities from which nothing, not even light, was ever supposed to escape, were slowly, quietly, and almost imperceptibly dying. Not violently, not in an explosion, not in a collision or a catastrophe. They were evaporating, leaking energy into empty space, one invisible particle at a time, across timescales so vast that the number of years required cannot be written in standard notation without filling several pages. And when the last black hole finally exhales its last breath, something happens to the universe that no human language was ever designed to describe. Tonight, we follow that breath, from the moment the first star collapses to the moment the last black hole disappears into silence. 18 chapters, one question. What happens at the absolute end of everything? If you enjoy our calm nighttime journeys through science and deep time, please like and subscribe. We highly encourage our community to share thoughts in the comments. It is always the most rewarding when we explore these ideas together. Now let us begin. Chapter 1. The Darkness That Eats Light. To understand the end, you have to understand what a black hole actually is. Not the word, not the cultural icon, what it is physically in the fabric of reality. When a star massive enough, roughly 20 times the mass of our Sun or larger, reaches its end of life, it runs out of fuel. For millions of years, nuclear fusion in its core has been generating an outward pressure that counterbalances gravity. The star is in a state of permanent tension, gravity pulling inward, fusion pushing outward, a balance maintained for millions of years across a sphere millions of miles wide. When the fuel runs out, the balance breaks. In less than a second, the core collapses. Material that had been spread across a volume the size of Earth compresses into a sphere roughly 12 miles across. The collapse happened so fast that the outer layers of the star, still falling inward, slam into the suddenly rigid core and rebound outward in the most energetic explosion in the known universe. A supernova. For days or weeks, a single dying star outshines every other star in its entire galaxy combined. Ancient astronomers watching the sky saw new stars appear where nothing had been before. They called them guest stars. What they were watching was the death scream of something far larger than anything they could have imagined. What remains at the center is a neutron star, a city-sized ball of matter so dense that a single teaspoon of its material weighs as much as all the mountains on Earth combined. But for the most massive stars, even that is not the end. Gravity continues to win. The neutron star collapses further, and at a certain point, the collapse passes a threshold beyond which physics as we understand it breaks down entirely. A singularity forms, a point of infinite density, a place where the known laws of the universe simply cease to apply. Around that singularity, gravity becomes so intense that the escape velocity, the speed an object would need to travel to break free from the gravitational pull, exceeds the speed of light. And since nothing in the universe can travel faster than light, nothing can escape. It doesn't matter, not radiation, not information. This boundary, the point of no return, is called the event horizon. It is not a physical surface. You could cross it without feeling anything unusual, but once you did, you would never come back. The universe outside would be lost to you forever. From the outside, the event horizon looks like a perfect sphere of absolute darkness. Light that passes too close bends around it and spirals inward, never to return. The black hole does not reflect, it does not emit, it simply absorbs everything that comes within reach and gives nothing back. For decades, that was the complete picture. Black holes were the universe's ultimate one-way doors. Matter went in, nothing came out. Then Hawking sat down with his equations, and in a single afternoon in Cambridge, the picture changed completely. Chapter 2. Quantum mechanics tells us something unsettling about empty space. It is not actually empty. At the quantum level, space seethes with what physicists call vacuum fluctuations. Pairs of particles constantly flicker into existence from nothing. A particle and its antiparticle exist for an almost unimaginably brief moment and then annihilate each other, returning their borrowed energy to the vacuum. These virtual particles are real. They have measurable effects. The Casimir effect, a tiny but detectable force between two closely spaced metal plates in a vacuum, is caused by them. Now, place this seething quantum vacuum right at the edge of a black hole's event horizon. What Hawking found was this: when a virtual particle pair flickers into existence right at the event horizon, something can happen that violates every prior assumption about these objects. One particle falls across the horizon into the black hole, where it is lost forever. The other escapes into space. And because the energy for this escaping particle came partially from the gravitational field of the black hole itself, the black hole loses a tiny, almost unimaginably small amount of mass with each such event. These escaping particles carry energy away from the black hole, energy that came from the black hole's own mass, And since mass and energy are equivalent, E equals mc squared, the black hole is evaporating.
The process is called Hawking radiation. The rate at which it operates is governed by the size of the black hole. Larger black holes evaporate slowly. The temperature of the radiation they emit, what physicists call the Hawking temperature, is inversely proportional to the black hole's mass. The bigger the black hole, the colder the radiation, the slower the evaporation. For a stellar mass black hole, the Hawking temperature is about 60 nanokelvin. That is 60 billionths of a degree above absolute zero. The cosmic microwave radiation, the ambient temperature of the universe left over from the Big Bang, is currently about 2.7 Kelvin, more than 40 million times hotter. A stellar mass black hole is currently absorbing far more energy from the background than it is losing through Hawking radiation. It is growing, not shrinking. But the universe is cooling. As it expands, the background temperature drops. Eventually, after an almost incomprehensible span of time, the universe will cool below the Hawking temperature of even the largest black holes.
And at that point, evaporation begins to win. Hawking's initial reaction to his own result was disbelief. He told his colleague Jim Hartley, expecting to be corrected. Instead, Hartley confirmed it. The mathematics was sound. Black holes evaporate. The most indestructible objects in the known universe have an expiration date. The physics community's response was initially skeptical, then stunned, then gradually, over years and decades, convinced. Today, Hawking radiation is one of the most widely accepted theoretical predictions in modern physics, despite never having been directly observed. The radiation from any macroscopic black hole is so cold and so faint that no instrument yet built or imagined could detect it against the noise of the cosmic background. We know it is real, we have never seen it, and it means that every black hole in the universe, from the smallest stellar remnant to the supermassive giants lurking at the hearts of galaxies, is dying. Just very, very slowly.
It is worth pausing here before we follow deep time forward to understand why Hawking's result was so revolutionary, not just for what it said about black holes, but for what it revealed about the structure of physics itself. Before Hawking, the laws of thermodynamics and the laws of gravity occupied completely separate domains. Thermodynamics, the science of heat, energy, and entropy, was developed in the 19th century to describe steam engines and chemical reactions. Its laws were statistical. They described the average behavior of enormous numbers of particles. They said nothing about individual particles and nothing about the geometry of space. Gravity, in Einstein's formulation, was a geometric theory. It described the curvature of space-time produced by mass and energy. It said nothing about heat, nothing about entropy, nothing about statistical behavior. The two frameworks had nothing to say to each other. There was no reason to expect a connection. Then, in 1972, Jacob Bekenstein, a graduate student at Princeton working under the supervision of John Wheeler, noticed something strange. He was studying black holes and realized that the area of a black hole's event horizon behaves mathematically exactly like entropy. When two black holes merge, the combined area of the resulting event horizon is always larger than the sum of the original two areas. This mirrors the second law of thermodynamics. Entropy never decreases. Bekenstein proposed that the entropy of a black hole is proportional to its event horizon area, not its volume, its surface area. This was deeply counterintuitive. Entropy is usually an extensive quantity. It scales with the volume of a system, not its surface. A black hole, if Bekenstein was right, stores its entropy not in the bulk of its interior, but on its boundary, on its skin. The physics community's initial reaction was dismissive. If a black hole has entropy, it must have temperature, and if it has temperature, it must radiate. But nothing escapes from a black hole. The idea seemed self-contradictory. Then Hawking did his calculation and found that black holes do radiate. The self-contradiction resolved. Bekenstein was right. Black holes have entropy proportional to their event horizon area. They have temperature inversely proportional to their mass. They emit thermal radiation. They are, in the deepest possible sense, thermodynamic objects.
The implications are still being unpacked today. If black holes obey the laws of thermodynamics, then thermodynamics is not just about steam engines. It is a fundamental feature of the universe at the deepest level. Connected to gravity, to space-time geometry, to quantum mechanics. This connection between entropy, gravity, information, and quantum mechanics is what modern theoretical physics calls the holographic principle. The idea, developed most fully by Juan Maldacena in his 1997 paper on the ADS-CFT correspondence, is that the information content of a region of space is encoded not in the volume of that region, but on its boundary surface. The universe is, in a deep mathematical sense, a hologram. The physics of three-dimensional space is encoded on a two-dimensional boundary. This principle means that the information paradox is not a paradox at all. Information cannot be lost inside a black hole, because information is not stored inside anything. It is always encoded on surfaces. The event horizon is not a one-way door through which information disappears. It is a surface on which information is written. And the Hawking radiation that slowly carries that information away is not random. It is, at the quantum level, a faithful transcript of everything the black hole ever absorbed.
Hawking's calculation did not just predict the evaporation of black holes, it opened a window onto the deepest structure of physical law. It suggested that information, entropy, and gravity are not separate phenomena, but aspects of a single underlying reality that we have not yet fully described. Keep that in mind as we follow the universe forward, because everything that follows, the long dying of matter, the isolation of the last black holes, the final evaporation, is not just a physical process, it is the completion of a thermodynamic transaction that Bekenstein and Hawking first described in a Princeton office and a Cambridge afternoon 50 years ago. Chapter 4. Now we need to understand the timeline, not in years. Years are useless here. We need to understand the structure of deep time itself. The universe is currently approximately 13.8 billion years old. That number, vast as it seems, is essentially zero on the timescale we are about to discuss. Cosmologists who study the deep future of the universe have developed a framework sometimes called the 5 Ages, a way of organizing the incomprehensible future into chapters of cosmic history. The first is the stelliferous era, the age of stars. We are living in it now. Galaxies are burning. Stars are forming from clouds of gas and dust, living their lives, dying, seeding the next generation. This era will end somewhere between 10 trillion and 100 trillion years from now, when the last red dwarf stars finally exhaust their fuel and go dark. 100 trillion years. That is 10,000 times the current age of the universe, and it is merely the opening act of the timeline we are considering tonight. After the last star dies, the universe enters the degenerate era, the age of remnants. Galaxies no longer glow. What remains are the cold, dark corpses of stars, white dwarfs slowly cooling toward absolute zero, neutron stars spinning down in silence, and black holes, the only objects still consuming whatever drifts within their reach. The degenerate era lasts from roughly 10 to the power of 14 years to 10 to the power of 40 years. For reference, 10 to the 40th is a 1 followed by 40 zeros. The current age of the universe, written the same way, is 1 followed by 10 zeros. The gap between those two numbers is not a stretch, it is an abyss. Then comes the black hole era. If protons eventually decay, as some theories predict, the last white dwarfs, the last neutron stars, and the last remnants of ordinary matter will crumble away into radiation and subatomic particles. What remains after that are the black holes. Only the black holes. For a period from roughly 10 to the 40th years to 10 to the 100th years, the universe is a vast, cold, dark sea of expanding space, with black holes drifting through it like embers slowly dying in an ancient darkness. They are the last structures, the last objects with any internal organization, the last things in the universe that are not simply a featureless, uniform sea of radiation and cold particles. And then, one by one, they die. Chapter 5. Before we follow the black holes through their long dying, we must acknowledge the possibility that none of it plays out as described, because the stage itself might be pulled from beneath the story. The vacuum of space is not simply nothing, it is a quantum field in its lowest energy state, or at least what we believe is its lowest energy state.
quantum field theory allows for the possibility that the vacuum we inhabit is not the true ground state of the universe. It may be a metastable state, stable enough to persist for billions of years, but not the absolute minimum energy configuration. A ball resting in a valley, but not the lowest valley.
A ball that could, if given the right quantum nudge, tunnel through the barrier and roll into a deeper valley. If our vacuum is false, if the true minimum energy state of the universe's quantum fields has lower energy than the vacuum we inhabit, then at some point, somewhere in the universe, a bubble of true vacuum will spontaneously nucleate. A tiny region of space will quantum tunnel into the lower energy state, and that bubble will immediately begin to expand. The wall of the expanding bubble travels at the speed of light. You cannot see it coming. You cannot receive any warning, because no signal can travel faster than the bubble wall. One moment you exist in the physics we know. The next moment the bubble wall passes through your location and everything changes. The laws of physics inside the true vacuum bubble are different from the laws we know. Atoms may not be stable. Chemical bonds may not form. The fundamental constants may have different values. Life, matter, structure of any kind, all of it instantly restructured into forms that bear no relation to anything in our current universe. The physicist Sidney Coleman described vacuum decay as the ultimate catastrophe. Not a disaster that destroys a civilization or a species or even a planet, but a disaster that destroys physics itself. The terrifying aspect is that we cannot know whether our vacuum is stable or metastable. The calculations are difficult in the extreme. The 2012 measurements of the Higgs boson mass placed the universe tantalizingly close to the boundary between stability and metastability. Close enough to make physicists nervous, but not close enough to make any reliable prediction about when, if ever, vacuum decay might occur. If it does occur, it will end everything instantaneously and completely, long before the heat-death timeline plays out. No gradual fading, no slow evaporation, just the bubble wall traveling at the speed of light, restructuring reality wherever it passes. Not the last chapter, the erasure of the book itself. But let us proceed on the assumption that our vacuum is stable, that the stage holds, and follow the story to its natural end.
Chapter 6. Not all black holes are equal. The ones formed by collapsing stars range from about 3 to roughly 50 times the mass of our Sun. They are enormous by human standards, but they are dwarfed by what lives at the centers of galaxies. At the heart of our own Milky Way sits Sagittarius A star, a supermassive black hole with a mass of approximately 4 million solar masses, 4 million times the mass of our Sun, compressed into a region smaller than the distance from Earth to the Sun. At the center of M87, the black hole that produced the first ever direct image of a black hole's shadow in 2019, sits a monster, 6.5 billion solar masses. Its event horizon is roughly the size of our entire solar system. and M87's black hole is not even close to the largest known. TON 618, a quasar remnant, hosts a black hole estimated at 66 billion solar masses. Its event horizon is so large that light would take 2 weeks to travel across it. These supermassive giants will be the last to die. Their enormous mass means their Hawking temperature is extraordinarily low, and their evaporation rate extraordinarily slow. For a black hole the mass of our Sun, the evaporation time is approximately 2 × 10⁻⁶7 years, a 2 followed by 67 zeros.
For a supermassive black hole of 10 billion solar masses, the evaporation time is approximately 10 to the 100th years. Physicists call this number a googol. It is a 1 followed by 100 zeros. Every metaphor breaks down at this number. Every comparison fails. Even saying that a googol makes the current age of the universe look like a single Planck time, the smallest meaningful unit of time in physics, barely scratches at the reality of what we are describing. But the physics is patient. Time at these scales is not our time. It is simply duration, and duration, given enough of it, is absolute. The largest black holes will evaporate. The question is only what happens when they do. Chapter 7. There is a moment worth pausing on, a moment that happens billions of years before the final evaporation, and that is, in its own way, just as final. Somewhere between 100 trillion and 1 quadrillion years from now, the last star in the observable universe will die. Not in a supernova, not in a spectacular collapse. The last star will be a red dwarf, the smallest, coldest, most miserly of all stellar classes. A sphere of hydrogen plasma, roughly 1/10 the mass of our Sun, burning so slowly and so dimly that it would be invisible to the naked eye from a few light years away. It will have been burning for trillions of years before it finally, quietly, exhausts its fuel. It will not explode. It will contract into a white dwarf and begin the long, cold fade toward darkness. When that last ember goes out, something happens to the universe that has never happened before in its entire history. There is no longer any source of light anywhere, not a single photon being actively generated by fusion, not a single nuclear fire burning anywhere across the entire observable cosmos. The universe becomes genuinely dark for the first time since the first stars ignited. Roughly 200 million years after the Big Bang. Think about what that means for any civilization that might have survived into the deep future. For billions of years, astronomers have looked at a sky full of stars, a sky that, however vast and cold the spaces between them, still glittered with evidence that the universe was alive with energy and process. In the degenerate era, those astronomers, if they exist, would look up at a sky with nothing in it, no stars, no nebulae glowing in the distance, just black, an absolute, unbroken, featureless black. And the only light would be artificial, generated, maintained, not found in the sky, but produced deliberately against the entropy of a universe that has stopped caring.
The physicist Freeman Dyson spent considerable effort thinking about whether intelligence could survive into the deep future of a cooling universe. His argument, published in 1979, was that consciousness does not require a fixed metabolic rate, that a sufficiently advanced civilization could slow its subjective experience to match the dwindling availability of energy, hibernating for increasingly long periods between increasingly brief moments of awareness, stretching a finite supply of usable energy across an infinite subjective experience. It was a hopeful argument, a remarkable one, and it was undermined decades later by the discovery of dark energy, the force accelerating the expansion of the universe. In an accelerating universe, the usable energy available to any civilization decreases not just because stars go out, but because the expansion eventually isolates every gravitationally bound system from every other. The observable universe shrinks. Resources become inaccessible not because they are used up, but because they recede beyond the reach of light. In an accelerating universe, Dyson's eternal civilization cannot exist. Infinite subjective experience requires infinite usable energy, and usable energy in an accelerating cosmos is finite.
So the last intelligent beings, if there are any, do not fade slowly into the darkness of the degenerate era. They face a harder limit, a horizon. Beyond it, the universe is not just dark, it is permanently, irreversibly impoverished. The energy that could sustain them has been carried beyond the edge of the accessible cosmos by the expansion of space itself. The last light goes out, and what follows is not merely darkness, but a qualitatively different kind of universe, one in which the thermodynamic conditions for life, for thought, for any process more complex than the slow cooling of isolated remnants have permanently ceased to exist. Only the black holes remain, and they are not lights, they are the universe's final patience, waiting across timescales that dwarf the age of stars for the mathematics of evaporation to complete its work. Chapter 8. There is something else happening in the darkness of the degenerate era that deserves its own chapter, something that strikes most people as impossible when they first hear it. The matter you are made of may be unstable.
Protons, the positively charged particles at the heart of every atomic nucleus, the particles that make up the bulk of every star, every planet, every biological cell, may not be permanent. They may decay. Not quickly, not in any way you would ever notice on a human timescale, but over sufficiently long periods, every proton in the universe may eventually transform into other particles and vanish. The Standard Model of particle physics, our best current description of the subatomic world, predicts that protons are stable, they do not decay. But extensions of the Standard Model, grand unified theories that attempt to unify the strong, weak, and electromagnetic forces into a single framework, generally predict proton decay. The rate depends on the specific theory, but the typical prediction places the proton lifetime at somewhere between 10 to the 33rd and 10 to the 36th years.
Experiments have been searching for proton decay for decades.
the Super Kamiokande detector in Japan, a tank containing 50,000 tons of ultra-pure water buried deep underground to shield it from cosmic rays, has been watching for the characteristic flash of light that a proton decaying would produce. So far, nothing. The experiments have ruled out the shorter proton lifetimes predicted by some theories, pushing the lower bound past 10 to the 34th years, but they have not ruled out proton decay. They have simply confirmed that if protons do decay, they are more patient than some models predicted. If proton decay occurs, the consequences for the degenerate era are total. White dwarfs, which are composed of carbon and oxygen nuclei, which themselves are composed of protons and neutrons, would not cool indefinitely. They would evaporate. Over timescales between 10 to the 32nd and 10 to the 38th years, every proton in every white dwarf, every neutron star, every cold remnant of ordinary matter in the universe would decay, releasing a slow trickle of positrons, neutrinos, and photons.
The white dwarfs would not go dark. They would glow faintly, impossibly faintly, sustained not by fusion, but the slow decay of their constituent matter. A white dwarf experiencing proton decay would emit roughly 400 watts of power, less than the output of 4 incandescent bulbs spread across a sphere the size of Earth, barely detectable but real. And then, when the last proton decays, the white dwarf is simply gone. Not collapsed, not exploded, dissolved. Its matter is converted into radiation and subatomic particles that disperse into the void. If protons do not decay, if the standard model is correct and protons are genuinely stable, then white dwarfs do persist. They cool for timescales that make the current age of the universe irrelevant. Given long enough, quantum tunneling could cause the iron nuclei in a cold white dwarf to rearrange themselves into a lower energy configuration. A white dwarf given roughly 10 to the 1500 years could quantum tunnel into a black hole. Not collapse into one through gravity, tunnel into one, a quantum event so improbable that its timescale exceeds the evaporation time of supermassive black holes by hundreds of orders of magnitude.
But time, as we have established tonight, is patient. Physics does not care about the size of the number, it only cares about the probability. And any non-zero probability given infinite time becomes certainty. Whether matter decays through proton decay or through quantum tunneling, the conclusion is the same. Everything that ever called itself solid eventually returns to radiation. The universe is not a collection of permanent things embedded in time. It is a collection of processes, each running at its own rate, each eventually completing its work and returning its energy to the general pool. The black holes are not an exception to this. They are the slowest process, the most patient, the last to complete. But they are complete. Chapter 9. We have talked extensively about what happens outside a black hole, the event horizon, the Hawking radiation, the evaporation. But there is a question we have been circling without addressing directly.
What is inside?
The mathematical answer is disturbing. At the center of every black hole, according to general relativity, there is a singularity, a point of infinite density, a point where the curvature of space-time becomes infinite, a point where the equations of physics do not merely give large answers, they give infinite ones. And in physics, an infinity is not an answer. It is a symptom, a sign that the theory being applied has broken down, that it is being pushed beyond the regime in which it is valid. General relativity predicts its own failure at the singularity. The equations break, the physics stops, and what actually occupies the point at the center of a black hole is genuinely unknown. This is not a gap in our knowledge that better observations could fill. We cannot send a probe into a black hole and receive data back. The event horizon is a one-way membrane. The singularity is, by construction, unobservable from outside. What we do know is that the singularity cannot be the final answer. A genuine physical infinity cannot exist in nature. Nature does not produce infinities. It produces very large numbers, but not infinities. Every time physics predicted an infinity in the past, the resolution came from a deeper theory that replaced the infinity with something finite. Quantum mechanics resolved the ultraviolet catastrophe of classical electromagnetism. The finite answer required a new framework.
A genuine theory of quantum gravity, the as-yet undiscovered framework that unifies general relativity and quantum mechanics, would do the same for the singularity. It would replace the infinite density with something real, something finite, something physically meaningful. Several candidates exist. Loop quantum gravity, a theory that treats space-time itself as granular at the Planck scale, predicts that the singularity is replaced by an extremely dense but finite region. In some loop quantum gravity models, the infalling matter does not terminate at a singularity, but bounces. The collapse reverses. The interior of the black hole becomes a new region of space-time that expands from the bounce, separated from our universe by the event horizon, inaccessible to us, but real. If this is correct, then every black hole contains a universe. Our own universe might be the interior of a black hole in some larger space-time. The Big Bang in this picture was not the beginning of everything. It was the bounce at the center of a collapsing region of a parent cosmos that we can never observe. String theory offers a different resolution. In the fuzzball picture developed by Samir Mather and collaborators, the singularity does not exist at all. The interior of a black hole is a dense, extended quantum structure, a fuzzball where quantum strings fill the entire region bounded by the horizon. There is no empty space inside. There is no singularity. There is only quantum structure. In this picture, the information paradox resolves naturally, because the information is encoded in the fuzzball itself and gradually released through radiation emitted from its surface. Neither loop quantum mechanics nor string theory has been experimentally confirmed. The interior of a black hole remains, in the most literal possible sense, unknown territory. But the question matters for our story, because if the singularity is replaced by a quantum structure,
then the final evaporation of a black hole is not the evaporation of a mathematical point. It is a real physical object. And when it finally goes, when the last quantum of mass is radiated away, what happens to that quantum structure? Does it dissolve with the rest? Does it leave a stable Planck mass remnant? Or does it simply become the final burst of radiation? Nobody knows. The final state of an evaporating black hole is one of the most actively debated questions in theoretical physics. And the answer, if we ever find it, will not come from observation. It will come from the theory we have not yet built.
Chapter 10. In 2015, for the first time in human history, we heard the universe. Not with ears, with instruments, the Laser Interferometer Gravitational Wave Observatory, known as LIGO. Two identical detectors, one in Louisiana and one in Washington State, each consisting of two perpendicular arms, 4 kilometers long, bouncing laser light back and forth to measure distances with a precision smaller than 1,000th the diameter of a proton. What LIGO detected was the gravitational wave produced by two black holes merging, objects roughly 36 and 29 times the mass of our Sun, spiraling toward each other across millions of orbital decay and finally colliding in a fraction of a second. The collision released more energy in that fraction of a second than all the stars in the observable universe emit in light during that same interval. And it did so not as light, not as particles, but as a ripple in the fabric of space-time itself. A gravitational wave that propagated outward at the speed of light, reaching Earth 1.3 billion years later as a distortion of space so small that LIGO barely detected it. What that detection told us was this: the universe speaks in gravitational waves. Every massive object that accelerates, every binary system that orbits, every merger that occurs sends ripples through space-time, and those ripples travel forever. In the stelliferous era, our era, the gravitational background is a constant, layered hum. Black hole mergers, neutron star collisions, the slow inspiration of binary stars. The universe is rich in gravitational radiation, and a detector sensitive enough would hear it as a roaring cacophony. But as the universe ages into the degenerate era, that cacophony fades. The binary systems that drive gravitational wave emission spiral together and merge, removing themselves from the background. New mergers become rarer as the density of compact objects in any given region of space decreases. And in the black hole era, that vast darkness where isolated black holes drift through a cold, expanding void, gravitational wave emission becomes rare in the extreme. Two black holes must drift close enough to capture each other gravitationally, a process that becomes exponentially less likely as the universe expands and dilutes. But it is not zero. Even in the deepest reaches of the black hole era, occasional mergers occur, and each one sends a gravitational wave pulse outward, a pristine, unobstructed signal
propagating through a universe with no other source of disturbance, a universe so quiet that this single wave, spreading outward at the speed of light, is the only sound in all of existence. And then it, too, fades, stretched by the expansion of space from its original frequency down through wavelengths that grow longer than the observable universe, diluted until its energy is spread across volumes too vast for any measurement. The last gravitational wave does not end. It becomes indistinguishable from the background. It joins the silence. The last sound the universe makes is one that no one will ever hear. Chapter 11. Imagine the universe at 10 to the 90th years. The stelliferous era ended quadrillions of years ago. Every star that ever burned has long since gone dark. Every planet has either fallen into a black hole, been ejected into the void, or slowly crumbled as its protons decayed. Galaxies no longer exist as structures. The gravitational threads that once held them together have been severed by the slow dissolution of matter, by the ejection of stars through gravitational interactions over eons, and by the relentless expansion of space that has been pulling everything apart since the Big Bang.
The universe is dark, not the darkness of a night sky dotted with stars, a different kind of darkness, an absolute darkness in which there is no light source anywhere across the observable universe. A darkness in which the average distance between any two particles grows with every passing moment as space itself continues to expand. Into this darkness the black holes drift. They are not entirely silent. They are still emitting Hawking radiation, but the radiation is so cold that it would be undetectable by any instrument we can imagine. For all practical purposes, they are dark, cold, and alone. Occasionally, two black holes drift close enough to merge. Each merger creates a larger object. In the early black hole era, mergers could temporarily reverse the shrinkage caused by evaporation, producing massive consolidated giants. But as the universe expands and matter becomes ever more dilute, mergers grow rarer and eventually cease entirely. Each black hole drifts in isolation across a universe of its own making, separated from every other black hole by distances that grow with every passing moment.
As the universe ages beyond 10 to the 90th years, even the most massive black holes begin to cross a threshold. Their Hawking temperature rises above the temperature of the surrounding universe, a universe so cold by this point that its temperature is effectively indistinguishable from absolute zero. At this moment, evaporation begins to dominate. And something counterintuitive happens. The evaporation accelerates. You might expect a black hole to evaporate at a steady rate, like an ice cube melting in a warm room, but physics works differently. As a black hole loses mass, its Hawking temperature increases. As its temperature increases, it emits more intense radiation. As it emits more intense radiation, it loses mass faster. As it loses mass faster, its temperature rises further. It is a feedback loop, a runaway process.
For most of its existence, a black hole evaporates with glacial slowness. Across googles of years, it barely shrinks. The process is so slow, it might as well not be happening. But as the black hole's mass decreases below a certain threshold, the feedback loop kicks in and the pace quickens dramatically. The final evaporation, what physicists call the death of a black hole, is not a slow, quiet fade. It is a burst.
In its final seconds, a dying black hole radiates with ferocious intensity. As the mass approaches zero and the temperature approaches infinity, the black hole emits a final blaze of high-energy radiation. Gamma rays, X-rays, a brief and brilliant flash against the cold darkness of the ancient universe. In its last fraction of a second, a black hole releases as much energy as millions of nuclear weapons detonating simultaneously. And then it is gone. Not absorbed by something else, not converted into another object, simply gone. The singularity, the event horizon, the warped space-time, all of it evaporates into a spray of particles and radiation that disperses into the surrounding void. What remains is something even stranger than nothing. Chapter 13. Here we arrive at the deepest mystery in all theoretical physics, a problem so fundamental that it has divided the greatest minds in science for 50 years and remains to this day unresolved. When you burn a book, the book is destroyed. The words are gone, the story is gone, but the information, the precise arrangement of molecules in the paper and ink, is not actually lost. In principle, with perfect instruments and perfect knowledge of physics, you could reconstruct every word from the smoke and ash. The information is scrambled beyond any practical recovery, but it is preserved. Quantum mechanics is absolute about this. Information cannot be destroyed. It can be scrambled, encoded, transformed, but never annihilated. This principle is called unitarity. Violate it, and the entire framework of quantum mechanics collapses. Now consider what happens when matter falls into a black hole, a star, a planet, a book, a human being. Everything that crosses the event horizon carries information. The precise quantum state of every particle it contains, and when Hawking radiation carries that mass back out as energy, the radiation appears to be purely random, thermal, without structure, without the encoded information of what fell in. If Hawking radiation carries no information, then when the black hole finally evaporates completely, the information of everything that ever fell into it is gone, destroyed, annihilated. But quantum mechanics says that cannot happen. This is the black hole information paradox. It is not a minor technical puzzle. It is a direct, irreconcilable conflict between two of the most successful theories in physics: general relativity, which predicts that information is destroyed inside black holes, and quantum mechanics, which says information destruction is impossible. Hawking himself initially argued that information was genuinely destroyed, that black holes were the one place in the universe where unitarity broke down. John Preskill of Caltech famously bet Hawking that information was preserved. In 2004, Hawking conceded,
announcing that he had found a mechanism by which information could escape through subtle correlations in Hawking radiation. But the precise mechanism remained unclear. In 2019, a series of papers using a concept called the island formula appeared to show that information is indeed encoded in the late-time Hawking radiation. The holographic principle we discussed earlier, the idea that the universe is a hologram and the event horizon is an information surface, then nothing is truly swallowed. Everything that falls in is written on the boundary and slowly read back out, encoded in correlations between particles emitted across billions of years.
The information gets out, but reading it is effectively impossible. Extracting it would require computational resources exceeding anything in the observable universe. What this means for the final evaporation of the last black hole is this: when that last black hole exhales its final burst of radiation, encoded somewhere in the quantum correlations between particles emitted across a Google of years, is the information of everything that ever fell into it. Every star, every planet, every particle of matter from the early universe that crossed the event horizon over billions upon billions of years. It is all still there, scrambled beyond any conceivable recovery, scattered across a universe too cold and too vast to read it, but there, preserved, not destroyed. The universe forgets nothing, even at the very end. Chapter 14. Here is where the story takes its strangest turn.
Maximum entropy does not mean nothing ever happens again. It means nothing organized ever happens again. Quantum fluctuations never stop. The vacuum seethes even in a universe at heat death. Particles flicker in and out of existence. Random configurations arise and dissolve. And here is the disturbing mathematics. In a universe that persists for long enough, and an accelerating universe, barring vacuum decay, persists indefinitely, any configuration of matter that is physically possible will eventually arise by pure chance, not because of any organizing force, purely because the number of possible configurations is finite and the time available is not. On timescales of roughly 10 to the power of 10 to the 50th years, a number so large that it makes a Google look like an afternoon, random fluctuations of the quantum vacuum will, somewhere in the cold, expanding universe, spontaneously produce a human brain. Complete, functional, with memories, with sensory impressions, with a complete subjective experience of being alive and conscious in a world. That experience will last for a fraction of a second before the fluctuation dissolves and the brain returns to the void. But during that fraction of a second, there is awareness, there is thought, there is a being that exists and experiences, and then does not.
These are the Boltzmann brains, named for the 19th century physicist Ludwig Boltzmann, who first described the thermodynamic fluctuations that, in principle, could produce them. And they are not a thought experiment. They are a genuine physical prediction. If the universe lasts long enough in a heat-death state,
more Boltzmann brains will arise, randomly, briefly, throughout the cold, expanding void, than the total number of observers who ever lived in the stelliferous era. If Boltzmann brains vastly outnumber ordinary observers, then any given conscious experience is statistically far more likely to be the flicker of a quantum brain than the product of billions of years of stellar and biological evolution. Your current experience, the one you are having right now, listening to this, should, by that logic, be overwhelmingly more likely to be a Boltzmann brain experience than the experience of an evolved observer on a planet orbiting a star. The fact that your experience is coherent, that your memories are consistent, that the world around you obeys regular laws, is, from this perspective, a statistical anomaly of breathtaking improbability.
Most cosmologists treat this as a sign that something is missing from our understanding of why the universe began in a low entropy state. The answer may require a theory of the initial conditions of the universe that we do not yet have. It may require understanding what preceded the Big Bang. It may require the kind of cyclic cosmology we are about to discuss, where each eon begins in a low entropy state, not by accident, but by the mathematical structure of the transition from one cycle to the next. Or it may require accepting that the universe is not eternal, that something ends the heat death before Boltzmann brains become the dominant form of observer. The question is not resolved. It hangs over cosmology as one of the deepest open problems in all of theoretical physics. And it is, at its core, a question about why there is something rather than nothing, and why that something is the kind of universe that produces genuine observers rather than quantum accidents.
Chapter 15. The last black hole dies. We do not know exactly when. The precise timing depends on the mass of the most massive black hole surviving to the end of the black hole era. If supermassive black holes of tens of billions of solar masses persist without merging into something larger, the last evaporation occurs somewhere around 10 to the 100th years, one Google. If black holes continue to merge throughout the black hole era, the timeline extends. Some theoretical scenarios place the final evaporation at 10 to the 200th years or beyond, but it ends. Physics is certain about that. And when it does, the universe enters the state sometimes called the dark era, or simply heat death. There is no more structure, no stars, no planets, no black holes, no atoms if the proton has long since decayed. What remains is a thin, cold, uniform sea of particles and radiation, photons of extraordinarily low energy, neutrinos, electrons and positrons, slowly annihilating on the rare occasions they drift close enough to meet. A faintest possible whisper of energy spread evenly across a universe that continues to expand, growing colder and more dilute with every passing moment.
The universe approaches but never quite reaches thermal equilibrium, a state in which everything is at the same temperature. Energy is spread perfectly uniformly, and no process can extract useful work from the environment. No engine can run, no chemistry can occur,
No complexity can form. Nothing can happen. This is what physicists mean by heat death. Not a temperature death, not a freezing death, a death of difference, a death of gradient, a universe in which everything is the same everywhere, and therefore nothing can change. The universe began in a state of astonishingly low entropy, highly ordered, highly structured, full of usable energy and sharp differences between hot and cold. The second law of thermodynamics says entropy always increases. The heat death is the final destination of that process. Maximum entropy, total disorder, the complete erasure of structure, but perhaps not the final word.
Chapter 16. Perhaps endings are not what they appear. Roger Penrose, the Nobel Prize-winning physicist at Oxford, has proposed a model called conformal cyclic cosmology. The essential idea is elegant and strange in equal measure. In Penrose's model, the heat-death state of one universe, a cold, featureless expanse of radiation in which all massive particles have decayed or annihilated, is mathematically indistinguishable from the state immediately following a Big Bang. Both are geometrically flat. Both are dominated by massless radiation. Both are, in a certain precise mathematical sense, the same kind of space-time. If this is correct, the end of one cosmic era is the beginning of the next. The universe does not end, it restarts. The heat death of our universe is the Big Bang of its successor. Roger Penrose calls each cosmic cycle an aeon. Our universe is one aeon in an infinite sequence. Before our Big Bang, another aeon played out. Stars burned, black holes formed, the last black hole evaporated, and that universe's heat death became our beginning. After our heat death, another Big Bang will arise, another universe will form, stars will burn again. Somewhere, perhaps, complexity will arise again. Perhaps minds will arise again.
Penrose has claimed to find observational evidence for this model in the cosmic microwave background, circular patterns of anomalously low temperature variance that he interprets as gravitational signatures of black hole mergers in the previous eon, imprinted on the beginning of our own universe. The claim is contested. Other researchers argue the patterns are consistent with random noise, but the model is taken seriously. It is published, it is debated, and it raises a possibility that physics rarely permits, that the death of the last black hole is not a tragedy, it is a contraction, a breath drawn in before the next exhalation, a pause between chapters in a book without a final page. Whether or not Penrose is right, the question his model forces us to ask is one of the most important in cosmology. Is the universe a sentence or a conversation? And it provides one possible answer to the Boltzmann brain problem. In a cyclic universe, there is no infinite heat-death state in which quantum accidents can accumulate to outnumber real observers. Each eon ends and resets. The low entropy beginning is not a statistical miracle. It is a structural inevitability built into the mathematics of the transition between cycles.
Chapter 17. We said earlier that the universe forgets nothing. Let us sit with what that means. Everything that fell into a black hole across the entire history of the universe, every star torn apart by tidal forces, every nebula consumed, every planet swallowed, every particle of matter from the dense early universe that drifted across the event horizon left its mark, a quantum imprint, an information signature encoded in the correlations between particles emitted across billions and billions of years of Hawking radiation. When the last black hole evaporates, that information is not destroyed, it is released, dispersed, scattered across the universe in the form of the final radiation burst and the subtle quantum correlations embedded in photons emitted across the entire evaporation lifetime. It cannot be read. Reconstructing the quantum state of a star from its Hawking radiation would require a computer larger than the observable universe, running for longer than the universe has existed. The scrambling is perfect, the decoding is impossible, but the information is there.
In the final radiation of the last black hole, encoded in its quantum correlations, is a record of the universe's history. Not a legible record, not a recoverable record, but a record. Every star that ever burned, every atom that ever bonded into a molecule, every moment of complexity that arose from the simplicity of the early universe, and then, over incomprehensible timescales, dissolved back into simplicity. The last black hole is, in a sense, the universe's final memory, and when it evaporates, that memory disperses into the void, still present, still encoded, simply unreadable. The universe becomes, for the first time since the Big Bang, perfectly still, perfectly complete. Every story is told, every process runs to its conclusion. Not death, completion. Chapter 18. So here we are at the end of this journey, or perhaps, as Penrose would have it, somewhere in the middle of an infinite one. We have watched a massive star collapse in a fraction of a second and birth a singularity from which nothing escapes. We have sat with Hawking as he found the error that was not an error, the calculation that should not have been possible, and understood through Bekenstein and the holographic principle why that calculation reaches all the way down to the deepest structure of physical law. We have traced the architecture of deep time across epochs that reduce the current age of the universe to a rounding error. We have stood at the edge of the last dying star and watched its light go out permanently. We have followed the protons through their own slow dissolution, matter itself returning to the radiation from which it came. We have looked inside black holes, at the singularity that physics cannot describe, at the quantum structures that might replace it. We have listened to the last gravitational wave propagate through an empty cosmos with nothing to receive it. We have followed the last black holes through their isolated vigil in a universe that has forgotten everything except them. We watched the final evaporation, the feedback loop quickening, the last burst of radiation against the cold darkness, the dispersal of a Google years of accumulated information into the quantum void. and we have asked the question that the physics keeps circling back to. Not how does it end, but what does it mean that it ends at all? The universe began in an extraordinarily improbable state, low entropy, highly ordered, full of structure and energy and the potential for complexity. The second law of thermodynamics has been driving it toward maximum entropy ever since, toward the heat death, toward the state from which nothing new can emerge.
But here is the insight that changes everything. That drive toward disorder, toward equilibrium, toward the erasure of structure, is also the engine of everything we consider beautiful. Stars burn because of entropy gradients. Life exists because of entropy gradients. Thought happens because of entropy gradients. The universe's slow march toward maximum entropy is not the enemy of complexity. It is the precondition for it. Every process, every star, every mind, every moment of wonder or suffering or love that has ever occurred in this universe has occurred because the universe had somewhere lower to go. And the black hole is the universe's most extreme expression of that principle. It collects, it accumulates, it preserves. It holds everything that falls into it, locked away in quantum correlations, held against the general dissolution of structure. And then, on timescales we cannot feel or imagine, it releases it all. The final breath of Hawking radiation, the dispersal of everything that ever mattered into a universe too cold and too vast to care. The last black hole dies alone in a universe that has long since forgotten why it began. And in its dying, it speaks in the language of quantum correlations, in the grammar of information that cannot be read, in the voice of everything that ever was. The universe receives the radiation, allows it to disperse, and continues expanding, indifferent, patient, already preparing, if Penrose is right, for the next Big Bang. And if he is not right, if this is all there is, if the heat death is final and permanent, and the last breath of the last black hole is the last meaningful event in the history of everything, even then it happened. We were here. We looked up. We asked. And for a universe that began as a quantum fluctuation in nothing, that may be the most remarkable fact of all. If you enjoyed this journey through the deep future, please like this video and subscribe to the channel. Your support makes these detailed explorations possible. Tell us in the comments if you could witness one moment in the far future of the universe, which would it be? The death of the last star? The final evaporation of the last black hole? Or the moment of the next Big Bang? And do you believe the universe cycles, or does it end? These are not questions only for physicists. They are questions for anyone who has ever looked up at the night sky and felt the weight of how much there is still to understand. Thank you for watching. We will see you in the next investigation.